Welcome to So You Want to Run Vault on Kubernetes, or in Kubernetes, depending on your preposition choice. I know some people are still filtering in. If you have empty seats next to you, please help people find a seat. Thank you all so much for coming. I realize that this is an odd time. For some of you, you're very hungry, and for some of you, you're very tired because you just ate. So it's the ideal conference talk spot. It's not. My name is Seth. I'm a developer advocate at Google. Prior to Google, I worked at companies like HashiCorp and Chef. You might recognize me from the DevOps versus SRE series that's pretty popular. I swear I own more than one shirt, but this is also the shirt that I wear in that series. You can find me on Twitter. My DMs are open. I'm pretty good at responding to people, although I've been drowning in messages at KubeCon. Thank you all so much for reaching out. My Twitter handle will be on all of the slides. If you have a question or if you want to DM me because you don't feel comfortable asking it publicly, feel free to do so. So we have a decent amount of content to cover today, and I promise live demos, so we'll get there. First, we're going to talk about Vault. I imagine that because most of you are in this room, you have a good understanding of what Vault is. For those of you that don't, I'm going to give you kind of a very quick crash course, but the majority of this talk is going to focus on Vault and Kubernetes. I just want to set a really strong base ground. Then we'll start with really part one, which is how do you run Vault on Kubernetes? Maybe you're a security team or a security architect and you want to provide Vault to your team as a service. How do you run this thing on Kubernetes? Then we're going to switch gears and we're going to put our developer or operator hat on and we're going to say, OK, I'm a person who needs to get secrets from Vault and I'm running my applications and services on Kubernetes. How do I authenticate? How do I get access to the secrets I need? So two different trains of thoughts. There'll be a very clear logical switch where we take off our security architect hat and put on our developer hat. And how do we configure Vault best to run in that architecture? And how do we connect to it in kind of the best secure way or the most secure way? So with that, let's go ahead and get started. Part one, we're going to talk about Vault. And again, I'm going to do this very quickly, so I apologize if you're already familiar with Vault. You can fall asleep for 2 minutes. If you're not familiar with Vault, I'm going to go very quickly just to get everyone on the same baseline. So what is a secret? We have Kubernetes secrets. That's not really what I'm talking about here. What is a secret? And there's kind of two ways that we can think about secrets. The first is that anything that can be used to authenticate or authorize. Most obvious example, username and password, an API key, TLS certificate. But then there's this kind of third or second classification of secret, things like a credit card number, a social security number, a passport number. And then there's a third classification of secret that are context dependent, things like a phone number, an email address, a home address. And all of these are really dependent on your business. So your definition of a secret if you work for the federal government might be different than a startup's definition of a secret. If you run the world's largest online cat meme website, email addresses are probably not something that you protect and encrypt, right? That's just a byproduct of the service you're offering. But if you're a company like MailChimp or a mailing list server, that's critical to your business. So you likely treat those email addresses with a little bit more scrutiny and a little bit more security. So when we accept the fact that every organization's definition of a secret is slightly different, we need a tool that's kind of flexible. So there are a lot of questions that come up when we're choosing those tools, like how does an application get access to a secret? It needs an API key to talk to some third-party service, or it needs a database username and password. But at the same time, humans also need access to those things, right? A local developer might be trying something out on their console or doing local development, and they need access to the staging or the testing database to make sure that their query is going to operate successfully. So how do we have both applications, services, computers, and humans access those same secrets? And then secrets are not static. I know this might be a shock to some of you, but they're dynamic. I like to say that secrets are like IP addresses. They come and go with the tides. So how do we update them over time? Maybe we're updating daily, weekly, biannually, but how do we update them and how do we ensure that that update is propagated across all of our systems? When it's leaked, how do we revoke it? Someone accidentally pushed something to a source control repository that's publicly accessible. How do we revoke that credential? And then given all of that, how do we know who's accessing a credential, where they're accessing it from, how they're accessing it, is it still in use? And what do we do in a compromise? What is our break glass situation? We have an Ashley Madison-style breach. We know that we are hemorrhaging data. It's better to incur downtime than it is to continue giving away our data to attackers. How on earth do we do that? Do we SSH into 1,000 systems? Do we just unplug the cord? Like, what is our break glass scenario? So Vault aims to be a single source of secrets that provides both machine and human-based access. So machines can authenticate via things like the API, and humans can interact via things like the CLI or the API if they prefer. And most importantly, it's designed to be cloud-friendly. So there are a lot of secrets management solutions out there. Vault happens to be open source and built for the cloud era, meaning it doesn't require like a hardware source of entropy like an HSM. So you can run this in any major cloud provider or on-premise if you'd like. Data is encrypted in transit with TLS 1.2 or later, and it's encrypted at rest with the latest cipher suites. And it operates on a hierarchical key value store. So if you're familiar with like GCS or S3, where you have folders, but they're not really folders, that's kind of how Vault is structured as well. So here's a quick example of interacting with Vault on the CLI. This is an example of putting some data into Vault and retrieving that data back out. This is using Vault's key value store. It's just, think of it like encrypted Redis or encrypted memcached. I put plaintext data in, Vault encrypts it in transit with TLS and at rest. And then when I want that data back out, I authenticate and authorize to retrieve the plaintext data. Everything that you do with the Vault CLI is also available via the API. That's going to be really important when we start talking about how pods and services are going to get access to these credentials. So here's that same thing, but done via the API using curl. So here you can see that same exact thing, slightly less of a nice human experience because this is designed for machines and computers. So we don't have as nice of a UX here, but all of the things that we can do via the CLI, we can also do via the API. And the reason for that is that the CLI is actually just a very thin wrapper around the API itself. So what happens in these break glass scenarios? These are real situations that people have encountered. An operator accidentally copies passwords.txt from the remote server onto their local machine during debugging. An application logs its database credentials to disk as part of a routine debug or a stack trace. You have a rogue package, like, I don't know, maybe in the NPM ecosystem that dumps your entire application's environment to some HTTP web server to do Bitcoin mining. Or a server includes an API token and a diagnostic output, right? Because a lot of these things are kind of insecure by default. We want to do our best to prevent this from happening, but we also have to accept the reality that it's going to happen. The unfortunate reality is that these are very real things that happen every single day. So we also need a plan for recovering for when these bad things happen. And we like to call this like a break glass procedure. Another way Vault gets around this is that in addition to having a kind of a static key value store, again, think encrypted Redis, encrypted memcached, it also has this concept of dynamic secrets. And this is where I like to challenge people to think of secrets like IP addresses. Just like when your laptop or your mobile phone connects to this conference Wi-Fi, you get an IP address from a DHCP server that's unique to you. When applications or humans connect to Vault and ask for a credential, they get a credential that's unique to them. And just like no two of you are sharing the same IP address, no two instances of your applications are sharing the same database credential. So it's a broker, in a sense, for secrets. This means that we have unique credentials, which give us a very, very tight audit trail between all of our services. We know exactly which instance of an application is using a particular credential, and we can quickly revoke just that credential without taking down our entire system. Just like IP addresses have a lease, those secrets also have a lease. They don't live forever. In addition to getting the credential, you also get time to use that credential, often called a TTL. And after that TTL expires, you have to go back and get another credential, or you have to renew the existing credential and ask Vault to continue using it. And access can be revoked earlier than that TTL in the event of a breach. And again, because we're issuing very specific like principal of least privilege style tokens and policies, when we revoke, we're less likely to take down all of production because we're not sharing one database password across all of our services. Instead, we're sharing nothing, essentially. So with this dynamic secrets, what happens is a human or a machine authenticates to Vault and requests some credentials. Vault then acts as a broker. It audits that request and then connects to that third-party service. That could be something like a Postgres or MySQL database. It could be an Oracle database. It could also be something like Google Cloud. We can generate IAM credentials. Or Amazon, we can generate access key pairs dynamically on the fly. It connects to that third-party system, whatever it might be, generates the credentials and returns them to the requester, assuming they've been authorized, and it audits that request. Each time the requester requests new credentials, they get a different set of credentials. So if you imagine your application boots, the first thing that it does is authenticates to Vault. Vault then goes out to whatever services you need, Postgres, MySQL, creates the user for you, returns a unique username and password. Your app then uses that for its lifetime. So here are some of the examples of what we call the secrets engines, or the dynamic secrets engines that allow us to generate these dynamic credentials. So there are major cloud providers, Google, AWS, Azure, pretty much every SQL standard database, as well as things like Oracle and MongoDB. And then I have this category of other, because I don't know where to put them, right? Things like RabbitMQ, TLS. Vault can actually act as your TLS root or intermediary. It can also manage SSH access for you, so instead of copying around authorized keys files and stuff like that, you can use and delegate that to Vault, things like Active Directory, et cetera. So I understand this was very quick, so if you're new to Vault, this is really the slide that matters, is that Vault provides authentication, authorization, and auditing, and it is a broker for secrets management. So Vault clients, those can be humans or machines, provide some sort of identity. That identity is mapped to policy. That policy then authorizes them to access 0 or more secrets. And from there, every secret that they access and every operation that they perform is audited. And that audit log is a rich audit log that's by default in a JSON format, so you can parse that and feed that into any logging or anomaly detection software that you have. So that's a very quick overview of Vault. So how do you run this thing on Kubernetes, right? So I'm sold on this idea of dynamic secrets. I'm sold on a bunch of Vault features we didn't talk about, like Shamir secret sharing. Or my boss just told me that I have to figure this out, and I came to this talk. So how do I run Vault on Kubernetes? Well, Vault operates in a client-server architecture. So clients are the local machines and the humans that are accessing the server. And then Vault itself runs as a stateful service in high availability mode, or not high availability mode, but you should run in high availability mode. So this architecture diagram shows how we would do it on Google, particularly Google Kubernetes Engine, but you could replace these, and we'll talk about the individual components in later slides here. So you run Vault in high availability mode. You put it behind a load balancer. It's your choice of whether that load balancer is public-facing or private-facing. And then from there, you use a highly available storage backend, and you use Vault auto-unsealing for extra availability. And all of that runs on top of Kubernetes, which gets us really cool things like auto-restarting in the event of failure. It can help us spread our Vault nodes, our Vault services across multiple nodes. So if one of those physical VMs dies, we still have availability. And it can help us auto-scale if needed. So what are some highlights from this architecture? So the first, and this is where I get contention, is a dedicated Kubernetes cluster. So Vault should always run in a dedicated Kubernetes cluster, which access is tightly controlled, ideally by your security architects or your security team. No other apps or services run in this cluster. Now, I know someone's like, well, what about namespaces? I'm very adamant, and this is my opinion, that you should run in a dedicated cluster, not using namespaces, but it's up to you. It's my recommendation that you run in a dedicated cluster, and I'll talk about that a little bit more in a bit. You want to use a highly available storage backend for Vault. So Vault has a number of different places that it can store data. They're all pluggable. So you have things like Google Cloud Spanner, Google Cloud Storage, Amazon S3, Amazon DynamoDB, the file system, in-memory. And each of those storage backends has different functionality that they expose. Some are faster than others. Some have this ability to support transactional interfaces. Some have support for high availability. The one that you're looking for particularly is support for high availability. You want to be able to run Vault in highly available modes. Even though you're running under Kubernetes, you want to have multiple nodes running simultaneously. Additionally, you're going to want to use a KMS-based auto-unsealer. Or if you're running on-prem Kubernetes, you can use an HSM-based auto-unsealer as well. This used to be an enterprise feature. This used to be a paid feature. It's now open source in Vault 1.0. You can use the open source version of Vault to do auto-unsealing via KMS. So what this means is when a new server comes online, it can join the cluster by using using keys that have been encrypted with a KMS provider like Google Cloud KMS or Amazon KMS. The next thing you're going to want to do is you're going to want to use a custom certificate authority for TLS. Absolutely under no situation should you ever communicate to Vault over anything other than TLS, 1.2 or higher. I generally use a custom CA because it's flexible. It gives you an additional level of trust because you can say, never trust the system certs, only trust this certificate. So you get kind of client and server-side validation. You could replace this with your own trusted PKI infrastructure, or you could delegate to something like Let's Encrypt. But you definitely want to use TLS. You're going to want to use L4 for load balancing instead of L7 for load balancing. The primary reason for this is that it delegates the TLS termination to Vault. And one of the ways in which machines can authenticate to Vault is with TLS. So they can present what's called a client certificate, and we can do mutual TLS authentication. If you're doing TLS termination at an L7 load balancer, it's going to terminate that connection, and then that client certificate is not going to be passed along to Vault. Or if it is, it's going to require a lot of additional configuration in that load balancer. So the L4 load balancer is going to be a little bit faster for us because we're at the TCP layer instead of the HTTP layer, and it gives Vault a lot more control over that connection. And then going back to why I think you should run Vault as a dedicated cluster is Vault is available via like that load balancer IP or DNS address. You don't actually want to expose Vault, or it's my recommendation that you don't expose Vault through the standard Kubernetes service discovery interfaces or any of the ecosystem tools that help discover services and route to services in Kubernetes. The reason for this is twofold. It makes signing those certificates very difficult because, again, you're not delegating to the load balancer, you're delegating TLS to Vault. So now you need to know every possible DNS address and IP that the cert needs to respond to put it in the SAN list. But at the same time, this practice really keeps Vault flexible. In the future, your company might want to migrate Vault to a different service. They might move from Kubernetes to some crazy new cluster scheduler that exists in 10 years. And if you're relying on the Kubernetes-specific features, that migration path is more difficult. So instead, I like to tell people, hey, think of Vault as like this thing that exists in an IP address when you're providing it to a service for your internal users. And then on top of all of that, and this is the last reason why I say you should run a dedicated cluster, is that you want to harden that cluster. These particular cluster hardening techniques might be too rigorous for your application clusters. But by running Vault in a dedicated cluster, you can really lock it down to just the minimum viable set of things. So things like TLS for everything, disabling HTTP basic auth and HTTP client auth, disabling the Kubernetes dashboard, making sure ABAC is off, only using RBAC, enabling pod security policies if you're running on a recent version of Kubernetes, network policies, et cetera. If you're running Vault in a shared cluster, you may not be able to enable these things because you might have applications that depend on these insecure functionalities. So that's another reason why it's beneficial to run it in a dedicated cluster. So when you run Vault, you're going to want to run it as a deployment or a stateful set. Previously, I was kind of advocating for a stateful set. We've been able to make it work very well with a deployment. So just a little bit faster to do it via a deployment, but you can use a stateful set as well. We're definitely going to want to use anti-affinity. By default, Kubernetes the scheduler is going to bin pack all of our nodes. So if we say, hey, run 5 Vault nodes, it's going to put all 5 of them on the first VM. And that's really not what we want, right? Because if that VM dies, we've taken our entire cluster offline. So we can leverage pod anti-affinity. In this example, I've used preferred, but you could also have required, where we want to spread those pods across as many VMs as possible. So if I have a node pool of, say, 10 VMs, I want 1 Vault running on each of them, not 10 Vaults running on the first one. That just gives me some added availability in case one node were to die. We want to make sure that we're giving the container IPC lock capabilities. If you give Vault the ability, if you give the container the ability to do memory locking, Vault will take advantage of that. This is, again, just an added layer of security. Vault will do memory locking when doing certain write operations in case someone else is on that process and is trying to page the memory. We're going to make sure that standbys return an OK status. By default, when you ask for the health of a Vault standby, it'll say, it will return a non-200 status code. And we're also going to allow uninitialized nodes to join our cluster. And that's solely so that we can route to them for the initial bootstrapping, which I'll show in a minute. And then we want a load balancer. And I'm not very opinionated on this. This is really up to you and your security team. In this example, I'm using a public-facing load balancer with the load balancer service. You could be using an internal load balancer. You could be using annotations to get this. You should be using a load balancer, though. At no point should you ever talk directly to a Vault pod. You should always be going directly through a load balancer. Whether that's private or public, that's entirely up to the security policies of your organization. So what does this Vault configuration look like? So this is where people get confused. There's 2 adder configurations in Vault. There's this thing called the API adder and this thing called the cluster adder. The API adder is set to the load balancer's address. The API adder is what Vault advertises that things should connect to it as. So this is the load balancer, because you should always go through the load balancer. The cluster adder is where Vault advertises to its peers where it lives, and this is the pod's IP address. So this is a key thing. If you're going to take a picture of any slide, you want to take a picture of this slide. And the way you get the pod's IP address is using field refs. So you can actually get that directly from a YAML spec. And I'll show an example of this in a second. You're going to want to bind to the pod's IP address when you listen as well. And then optionally, you might want to listen on localhost without TLS. This is useful if you're kind of getting started learning about Vault, because you can exec into the pod and run Vault commands directly without having to set a bunch of environment variables or specify flags or disable TLS verification. As I said before, you're going to want to use HA storage. So here's 2 examples. There are many storage backends that support high availability. And you'll want to leverage Vault 1.0's auto unsealing. If you're running a version of Vault that's pre 1.0, I highly recommend you upgrade. There's a lot of new features, but this is one of the best ones. So what this will do is it'll store our unseal keys in Vault, encrypted by KMS, and when a new node joins the cluster, assuming it has access to that KMS key, it will automatically join. So now we'll do a demo. Who's excited? There's one person that's excited. That's cool. All right, so let's take a look at some YAML. So this is the full expanded kind of YAML is what I just showed you. There's our load balancer. Obviously, the IP is different. One of the things I don't talk about in the slide is that I'm binding, kind of mapping port 443, which is the standard SSL port, to port 8200. I'm up in the air of whether I want to call this a best practice. The reason I do this is that most hotel and conference Wi-Fi doesn't allow access on random ports. So 443 is a safe one. The second is that I work with a lot of enterprises, and it's actually really hard for them to open up ports, and 443 is also always open. So especially if you're doing a hybrid cloud, multi-cloud thing, 443 is like less likely to run into just weird security issues that you might pop up or weird firewall rules. So here I'm using a deployment. I'm deploying 3 Vault nodes. Again, there's our anti-affinity rules. Here I'm running Vault 1.0 directly from Docker Hub with the server. There's that IPC lock capability. The container itself is still running on 8200 and 8201 for the cluster ports. Some memory requests. We give it our TLS certificates. Here's that field ref I talked about before. And then here's how you reference that field ref by applying the configuration directly in the pod spec. So Kubernetes will actually interpolate that for us. We don't need to use Helm or another template provider for this. GCS, TCP listeners, and again, I'm also listening on localhost just for debuggability. And then at the very bottom here, we have our readiness probe, and we mount our TLS cluster. This is all open source. It's on GitHub. I'll tweet out the link in a bit, because I know I'm going kind of fast. So config, get context. All right, so I'm going to apply that. And here's hoping for conference Wi-Fi. You can do it. So while this is going, what's actually happening is it's attempting to post this pod spec to the internet. It's happening. It's happening. Or it's not happening. It's fine. This is like the awkward silence of live demos. OK, well, we'll move on. So hopefully that'll be done when we get back. But the next section is all about connecting to Vault from Kubernetes. So hopefully when I come back, that will be running. And let's imagine now, let's completely forget that Vault is running under Kubernetes. It could be running on Heroku or on-premise. It's just a thing and an IP address. Again, this is why the load balancer and dedicated cluster is so important. So forget everything. Again, imagine that it's like a SaaS that's provided to you and that Kubernetes is just an implementation detail. And I really think that this is the best way that organizations should think about running Vault. Don't expose it through Kubernetes. Don't use Kubernetes-specific things. Leverage Kubernetes functionality to make Vault more available and more resilient, but it's just a thing in an IP address. So let's talk about this authentication thing. So in order for humans or applications to communicate with Vault, they need this thing called a Vault token. You can think of it like a session ID or a cookie for a website. So just like on a website, you give a username and a password, and that gives you a cookie, a session ID, which is stored in a cookie in your browser. We need to do the same thing to Vault. So I'm going to provide Vault some information, might be a username and password. Vault's going to verify that with a third-party system, might be Active Directory. Assuming that's successful, we're going to do kind of a lookup in the database to see what permissions I have. Am I an admin? Am I a general user? And then I'm going to get back a token that has all of those policies mapped to me. In the case of Kubernetes, we actually use the pod service account, specifically the JWT token, the JWT token for that service account, and the token reviewer API. So we configure Vault to have permissions to talk to the token reviewer API. A pod launches, grabs its service account from the file system usually, posts that service account JWT token to Vault. Vault verifies the identity of that pod as well as its namespace in the service account with the token reviewer API. Assuming that's successful, that is then mapped to policy. A Vault token is then returned to the service account, to the pod that requested it, and the pod uses that token for further requests, the same way that you would use like a session ID or a cookie to make further requests to the browser. Okay, demo 1 didn't even finish, and my slides tell me I have to do demo 2. Unable to find server. Can y'all do me a favor and make sure you're not on the Wi-Fi? I'm pulling like a Steve Jobs here. I need everyone off the Wi-Fi. Let's try the 2.4 gigahertz. No one uses 2.4 gigahertz. Aha! Yes. Don't thank me. Thank 2.4 gigahertz. All right, so we're just waiting for these to boot. Usually takes about 10 to 15 seconds. Hopefully that wasn't just a sporadic success. It might have been a sporadic success. See, I normally have a backup plan for this, which is that I tether my phone, but I have no service in this room either. So it's really exciting. Let's try it. Man, this just ruins everything. I promised live demos, and I don't have any now. All right. OK. It's still creating this container, man. Really? I think it got stat. OK. Let's try this again. It's going to work. Because if it doesn't work, it's kind of awkward. What's that? Yeah. I haven't created a secret yet. See, y'all are smarter than me. What are these named? Vault.key equals GLS vault.key. Okay. ca.cert, vault.key, vault.cert. Okay, let's try this again. Don't think me, it was his idea. Okay, and they're ready now. So now what I need to do is, in 3 minutes, do the rest of my demo. All right, so we're going to initialize this thing. So make sure that we can talk to it. We'll run vault status, and it'll come back and say, hey, it's not initialized and it's currently unsealed. So what we'll do is we'll run vault operator init. And this will give me my initial root token and 5 unseal keys. I'm not going to dive into exactly what those mean, but I'm happy to talk about them offline. OK, cool. So I get this initial root token thing. And I'm going to open up my vault env and export that as my vault token and source that again. And now when I run vault status, we should see that it's initialized and unsealed. So initialized is true and sealed is false. Thanks for double negatives. So what I'm going to do now is I'm going to put a secret in. I'm just going to call the secret KubeCon, and the message is hello. And we can get that secret back out. And yay, how many people feel more secure? I don't. Cool, so let me switch to, again, dedicated cluster. I'm going to switch to my other cluster. So I have this cluster here called my apps cluster. Config, use context, that. And there's nothing in here. Hopefully there's nothing in here. It'd be weird. All right, so there's nothing in this cluster. And what I'm going to do is I'm going to use this fancy script that I wrote because I suck at typing. And I'm just going to walk you through it very quickly. So the first thing I'm going to do is I'm creating a service account. And then I'm creating an RBAC binding for that service account to be able to talk to the token reviewer API. Here's where things get a little bit hacky, mostly because of a bug in JSON path. But I'm getting the token, the JOT token for that secret that we just created for that service account. And I'm getting the cluster name from my Kubernetes config and the actual host, as well as the CA cert, because those are all things that we give to Vault. Glossing over details here, here's the important part. We give Vault the Kubernetes host, the IP address, to our apps cluster, the CA cert to communicate with that cluster, and the JOT token for the service account, which can actually communicate with the token reviewer API. Vault will use those 3 pieces of information to validate any pod service account that it's given against the token reviewer API. Next, I'm just creating a simple policy in Vault that lets the secret read-only policy the ability to read from secret. And then we create a role in Vault, where in this example, I'm just binding to the default service account and the default namespace, but you can create multiple roles and create multiple mappings here. And then anything that matches this policy, this role, will get the policy secret read-only. And I'm also uploading our TLS secret for real this time. And then I'm I have to give the Vault address to these pods because they don't actually know where Vault lives because it's just a thing in an IP address. So I'm going to run this and hope that the bandwidth holds out. OK, so now I'm going to do demo shell. I know we're over time. This is how you know I'm not faking it. OK, so I'm like pretending to be a pod right now. I'm just in a Debian container in Bash. And I'm going to show you what a pod would have to do to authenticate to Vault. So the first thing I'm going to do is run app-get update. See, this is fast because it's not actually on this network. I'm going to install curl and JQ. Look how fast this is. Look how fast I type. It's like the Matrix. All right, so our JOT token, who knows where that lives? It's OK, I know where it is. var run secrets, Kubernetes IO, service account, token. All right, so now when we echo our JOT token, we get a JOT token. I need to take that JOT token and give it to Vault with the role that I've requested, and Vault will give me back a Vault token. So I can curl Vault adder v1 auth Kubernetes login. And my role, what do we call a role? Demo. And my JOT token is that thing that is in my environment. Really? Oh. Did have braces, didn't it? OK, cool. And I get back this payload from Vault, which includes a bunch of information. But the only thing I care about is this client token, which is like my session ID. And from here, I can run curl with that as my header for my Vault token. And I can ask, hopefully, for the secret named KubeCon. And I get back the message from hello. So I know that we're out of time, but that was also really hard. In fact, I have a slide with 3 question marks on it, because that was like a lot of work. You're welcome. I put all of that functionality into a pod that you can put in an init container that automatically pulls that service account and drops it in an in-memory volume. And then all you have is that Vault token. So you don't actually have to do all of the stuff I just did. I've automated it for you, but I wanted to show you the hard way. The easy way is to just use this container. It's open source, so you can audit it. You can build it yourself if you don't trust me. I wouldn't. Another tool that I want to mention is this tool called Console Template. Console Template will actually help you extract multiple secrets from Vault. Maybe you have a TLS key and a couple database passwords, and you have some legacy Java application that just really wants to consume a POM XML file or a properties file. You can use Console Template to render out that properties file, meaning your app doesn't have to be Vault aware. And then Console Template can actually communicate with your application when those secrets change. So it's just writing out a file in a shared volume that your app is consuming. Which always brings up a big question, which is like, how do I know if my credentials change? How will my app know to reread its config? There's a cool beta feature called shared process namespaces in Kubernetes 1.10. If you enable this, this will allow multiple pods to communicate with one another, so they're not all running as PID1. They're actually sharing a process namespace. You give ptrace, which allows you to call PID-of, and then basically Console Template is sharing a process namespace. So it has the ability to signal your application when it has updated that configuration file. and then your app can be restarted, respond to a signal, wholeheartedly blow up, whatever your choice is whenever that config file changes. Here's more information. Thank you all so much. Sorry I went over time. I'll be around for questions.